Greetings and welcome to the Nomenclature Lab for Chemistry 151. This lab is going to introduce the most common forms of naming that are used in chemistry, so you'll be able to name chemicals. You'll be able to talk the talk, if you will, of the chemists. Should be a pretty cool lab. We're going to learn how to name compounds. And gosh, one extra atom or one fewer atom makes an incredible difference when it comes to the reactivity. You've got to know which chemical you're talking about before you start adding it in. And in the old days, this was a problem. When they didn't have rules, you might add the wrong kind of chemical. And we'll talk about examples of this during the lecture. But anyway, in this lab and in this little intro, what I want to do is I want to introduce the three most common kinds of nomenclature. And they're called nonmetal, which is when nonmetals come together and they use what's called covalent bonding and Greek prefixes, which we'll talk about later. There's also what they call fixed charge metal and nonmetal compounds, which is where you have ionic bonding. Variable charge metal and nonmetals is another type, another ionic form of bonding that's going to use some Roman numerals to help us figure out what's going on. And then we'll overview real quickly polyatomic ions and also talk about acids and bases, all things really important in chemistry. So let's get into it. But before we do this, we've got to know where the metals and nonmetals and stuff like that are on the periodic table. So here's a little cheesy graphic and stuff, overview of the periodic table. And the blue elements, the ones mostly in the upper right corner, but also hydrogen, those are what they call the nonmetals. Nonmetals like to share electrons more than anything. They're usually good. They will be negative with metals, and that'll be important to us coming up. Metals are all the red elements, and you can see there's just a ton of metals on the periodic table. They outnumber the nonmetals big time. Metals like to give up electrons, especially to nonmetals, and they're going to be the ones which are usually positively charged. There are a little series there of yellow elements called metalloids. Metalloids can act both as metals or nonmetals, depending on what's around them. So nonmetals are easy. They like to take electrons, share electrons. Metals like to give up. The metalloids can do both. Kind of depends what's around it. We're not going to deal so much with metalloids, but anyway, if you do run into a metalloid, sometimes you'll see those expressed in multiple systems. Covalent and ionic bonding were terms we talked about earlier, and I want to do just a real fast overview of that too. Covalent bonding is sharing electrons. It's kind of like a handshake when you shake someone's hand. You each have a hand, it goes together. Well, in a covalent bond, the atoms are sharing their electrons through like a handshake. And here's an example, for example, of ammonia, NH3, and I'm circling that one part right there. You can see there how the nitrogen has the red electron and the hydrogen has the blue. And those two electrons make the bond, the covalent bond between the two atoms. It's not really fair to say that the nitrogen has all the electrons or the hydrogen does. They're sharing them equally, and that's what covalent bonds are. Mostly covalent bonds are in nonmetals, so nonmetals. But we are going to deal a lot with ionic bonds. And in an ionic bond, something has to lose electrons. So here's sodium becoming a sodium ion, or what's called a cation, a positively charged ion. Now, sodium has 11 protons and 11 electrons normally. When it makes an ionic bond, it loses an electron. That's what that little guy is right there. And you can see how it goes from 11 electrons to 10 electrons. And if you have fewer electrons, you're going to start seeing positive charge. So positive charged sodium pops in. Electrons usually they'll go somewhere, and that electron is going to be added to a nonmetal. So in this example, a chlorine atom, which has 17 protons and 17 electrons, is going to gain that electron. Now it has 18 electrons, but still only has 17 protons. You've got more negative charged species than positive ones. This is when you're going to have negative ions, or what's called an anion. This is called a chlorine anion, an ion. Ionic bonds, the positives, negatives, are much stronger than the covalent bonds, all right? Take a lot more energy to break up. However, don't think that covalent bonds are useless. Covalent bonds are much more flexible. And our life, our DNA, our sugars and caffeine and things like that, you've got to have flexible bonds, and that's where covalent bonds are really helpful. They're both really important. They're both going to have a lot of uses for life and all the things we do in it often. So let's look at the nomenclature of nonmetal and nonmetal compounds. So in this kind, you're going to use things just from the upper right-hand corner. There's going to be no metals in this one. And if you have nonmetals coming together, that's when you're going to get into those covalent bonds where the electrons are shared. And nonmetals are usually not too hard to name. The order of the nonmetal complex is important to chemists. And believe it or not, the first atom listed is the one which is more metallic. It's more like a metal than the second element that's listed. The second element listed is less metallic. So as an example, carbon dioxide is always carbon listed first and oxygen listed second. It's never dioxygen carbon or something like that. That's because the carbon, we're going to see in future courses, is the more metallic atom, and the oxygen is the less metallic. And that actually makes a big difference when it comes to chemistry. Now, the element which is less metallic, we're going to change its name and give it an IDE ending. So earlier, I said carbon dioxide. We changed the oxygen to an oxide, all right? And that's what you do with these kind of things, especially the second ones. So the second element, we'll get it. Nitrogen dioxide, maybe you've heard of that. Another example of oxygen becoming oxide. You always want to change it. And finally, because a lot of these things have more than one combination of atoms, we're going to use Greek prefixes to tell how many atoms you have, all right? The first one usually doesn't have a Greek prefix unless you have more than one, but you always use a Greek prefix on the second atom. So earlier, I did say carbon dioxide, all right? The carbon didn't have a Greek prefix because there's only one, but I said dioxide. Di means two. It's one of the Greek prefixes you can see there on the left, and di means two. So carbon dioxide means one carbon, two oxygens, and the oxygen turned to oxide means it's less metallic. Carbon monoxide is another compound. Carbon monoxide has a mono. That's Greek prefix for one. So that has one carbon and one oxygen in it. So let's look at some examples. People usually pick this up pretty well. CO2, we saw carbon dioxide, one carbon, two oxygens, oxygen listed second, so it's more, it's not into metals, it's not metallic, so we're going to call that an oxide, and because there's two of them, it's a dioxide. And again, CO would be carbon monoxide, and if you write it monooxide, it's okay, but usually double vowels are eliminated, but it's not a big deal. Carbon monoxide would be one carbon, and monooxide, one oxygen to go along with it. Now, if the first atom listed has more than one atom, then you do put a Greek prefix in it. So the formal name for water, H2O, dihydrogen, because there's two of that more metallic element in it, monoxide, one oxygen, all right? So notice that the second element always gets a Greek prefix, but the first one, you only give a Greek prefix if there's more than one, all right? Now, water is an example of a common name, and obviously water is easier to say than dihydrogen monoxide, but when you get formal about rules and stuff, dihydrogen monoxide is the official name for water. So this is a good way of how you turn formulas into names. Now you can go the other direction. You can turn names into formulas. So nitrogen dioxide would be one nitrogen, two oxygens, and definitely put the oxygen second because it's less metallic. Nitrogen dioxide. Dinitrogen monoxide would be N2O, two nitrogens, di-nitrogen. Monoxide means one oxygen, and again, the oxygen is listed second. Don't write it ON2. That would drive me and other chemists crazy. Dinitrogen tetraoxide would be 2 nitrogens. Tetra is 4, so 4 oxygens, N2O4. And so these rules, pretty chill, pretty easy to do. Once you get used to the Greek prefixes, it's pretty good. In chemistry, we mostly just go up to 10. More often than not, like 8 or less is what we use, but it's good to have these in case you need them, no problem. But these rules are only for nonmetals plus nonmetals. Now we'll look at some examples of what to do when the metals get put in. Now, when you do have a metal, you change the bonding. You go from the shaking of hands or the sharing of electrons, and you go into full positive and negative charges. And this is where the ionic bonds come in. And ionic bonds are super strong. Now remember, the metal is going to be the one with the positive charge, and the nonmetal is going to be the one with a negative charge. Now, when you have positives and negatives running around, they're so reactive that you want to make sure you balance positives and negatives so that nothing is left over. So if you have a positive one, you want to have a negative one to go along with it. If you had a positive 2, you could have 2 negative 1 charges, or you could have 1 negative 2, but you want to make sure all the charges go to 0 at the end. So balancing the positive and negative charges is really important in this section. Some of the metals have fixed charges, which means we know what their charge is all the time, or 99.999% of the time, something like that. So we know what they are, and there's quite a few of them, all right, that we feel as chemists are comfortable, we know what their charges are. But there's a lot of them which are variable, like sometimes they'll be positive 2, and then other times they'll be positive 3. And they exist in these different variations enough that it's good to talk about how to figure them out. So we're going to separate this next section into fixed charge metals and variable charge metals. And the nice thing, though, is that the nonmetals always have fixed negative charges. So if you don't know what the metal's charge is, you can use the nonmetal's charge to figure it out. Because remember, all the positives have to balance all the negatives. And that's going to be really important to us coming up. So let's talk about what the nonmetal charges are and also what the fixed charge metals charges will be too. So here's an example of how to find the non-metal charges. And the punchline is that you're going to need a periodic table. You take the group number of the non-metal and you subtract 8 from it. So as an example, if you want to figure out what the charge is on a phosphorus when it's in contact with a metal, phosphorus is in group 5A. So 5 minus 8, phosphorus as an ion will always have a negative 3 charge. And that's really powerful and cool as a chemist, because the phosphide ion, remember we're changing the more negative one to the IDE, it's less metallic. Phosphide is what you call it, would be a P negative 3. And anytime you see a phosphide ion, it's going to be P negative 3. And phosphorus by itself will have a negative 3 charge. So down here are just some of the more common kind of non-metal ions. You can see in group 7A on the far right, the halogens. Those would be fluoride, chloride, bromide, and iodide. All of those are going to have group number 7 minus 8. They're all going to have a negative 1 charge. And we're turning them all to IDE because they're going to be the negatives. Group 6A right next door, oxygen becomes oxide, and 6 minus 8, negative 2. Sulfur becomes sulfide, 6 minus 8, negative 2. Below that, we would have the selenide ion, which is not on here, but you can put it on there if you want. Se minus 2. Everything in that group, negative 2 charge. Selenide, sulfide, oxide, telluride would be below that. Now, group 5A, 5 minus 8, nitrogen becomes nitride, phosphorus becomes phosphide, arsenic becomes arsenide, etc., etc. And once in a while you'll see group 4A's, carbon becomes carbide, 4 minus 8, negative 4 charge. All right. Make sure you're using the periodic table with groups A and B. I call it the American version of the periodic table. So it'd be 4A, 5A, 6A, 7A. There's also an international group. You'd have like 17 over 7 and over 7A. It's the same idea, 17 minus 18, but I'd prefer that you use the quote-unquote American version where the group numbers are shown as is. Email me if that's confusing. Fixed charge metals. There's basically two sections where we know the charge all the time. And the sections, one of them groups 1A and 2A on the far left side of the periodic table. And there's also something called the stairs. And these sections on the periodic table are metals with fixed charges. We always know what their metals charge is. Groups 1A and 2A, the charge is literally just equal to the group number. So sodium, as an example, is number 11 on the periodic table, but it's in group 1A. That's the important part. And because of that 1 of 1A, that means sodium as an ion, always positive 1. And calcium, which is right next door in group 2A, will always be positive 2. So that means, for example, then potassium, K, right below sodium, would be positive 1. Magnesium, right above calcium, would be positive 2. Everything in group 1A is positive 1. Everything in group A, positive 2. In addition to those two groups, there's also what they call the stairs. And if you look at the periodic table, start with aluminum, number 13 on the periodic table. There's like a 3-step and then 2-step and then 1-step. And all those 6 metals have fixed charges. The 3 in the first step, aluminum, gallium, and indium, are always positive 3. The second step with 2 steps, those are always positive 2, zinc and cadmium. And finally, silver, which is the single step, silver is always positive 1. So the 6 stairs metals plus groups 1A and 2A, those are the fixed charge metals, and we know those all the time, and that's going to be important to us. If you want to start naming things, we're going to look at examples here with fixed charge metals. So let's say we wanted the name of NaCl. Well, Na, group 1A, a fixed charge metal with a positive 1 charge. Chloride is in group 7A, 7 minus 8, negative 1. That would be sodium chloride. I didn't really need to even figure out the charges on these. Notice that. I just called the metal as it is, non-metal with an IDE ending. So here's MgBr, magnesium bromide. But notice how there's 2 Brs for every Mg. That's because magnesium is positive 2. And bromide, group 7 minus 8, bromide is negative 1. So you're going to need 2 negative 1 bromides to cancel the Mg plus 2. But naming them is pretty chill. Aluminum oxide is Al2O3. And again, for fixed charge metals, you can literally just name of metal, name of non-metal, IDE. Notice the numbers though. You have 2 aluminums, 2 positive 3 aluminums. Aluminum's one of the stairs. And oxygen is negative 2 on the periodic table, and there's 3 of them. So 3 negative 2 oxygens is balanced by 2 positive 3 aluminums. Everything's neutral. Aluminum oxide, Al2O3. Now let's go the opposite direction. Let's start with a name and go to the formula. So Ki is the formula for potassium iodide, and that's because potassium is a positive 1 group 1A metal, and iodide is a group 7A nonmetal. Iodine becomes iodide, negative 1. 1 positive 1, 1 negative 1, or 1 plus minus 1 goes to 0. Ki is the right formula for potassium iodide. Potassium oxide, we still have positive 1 potassium, but now we've got oxygen. Oxygen's in group 6, 6 minus 8. Oxygen is always going to be negative 2. So we need 2 positive 1 Ks to balance that negative 2 oxygen. K2O is the formula for potassium oxide. And finally, gallium sulfide. Gallium is one of the stairs. Gallium is positive 3. And sulfur, which is right below oxygen, group 6A, sulfide, negative 2. So if you have 3 times 2, you're going to get 6. So notice that for gallium, that means positive 3 gallium times 2 is going to give positive 6. For sulfur, negative 2 sulfur times 3 is going to give -6. Gallium sulfide, Ga2S3. Again, you want to make sure that your overall charges cancel out when you're done with your formula. Most of the metals, unfortunately, are not in groups 1A, 2A, or the stairs. And all the metals that aren't there, and that includes all the transition metals, lanthanides, actinides, and even some metals under the nonmetals. All of those metals are called variable charged metal cations. They're going to be positive, but we don't know what their charge is going to be. Like sometimes they'll be +2, and sometimes they might be +6. So all of these metals, we need a way to tell other chemists what the charge is. And that's where the Roman numerals are going to come in. And in the lower left-hand corner there, you see the Roman numbers for 1 through 10. In chemistry, we use 1 through 7 quite a bit. We do see other ones, but those are the ones to pay attention to. If you haven't used Roman numerals for a while, number 4 and number 6 look really close to each other. So make sure you know 4 from 6. That's the most troublesome spot of these by 4. 4 is IV and 6 is VI. I know it's kind of strange. Here's some examples of how we can use it. Chromium and iron are both in the transition metal region of the periodic table. They're both variable charge. And sometimes, for example, chromium is +2 and sometimes it's +3. So if you're going to talk to a chemist about a chromium with a +2 charge, you would refer to it as chromium Roman numeral 2 in parentheses like that. Chromium with a +3 charge would be chromium Roman numeral 3. And again, notice the parentheses. Those are really important. Here's some examples with iron. Iron +5 would be iron with a Roman numeral 5. And iron +6, iron with a Roman numeral 6 by it. Let's say we wanted to name FeCl2. Well, iron is a variable charge metal, and we don't know what its charge is. So when you see something like this, start with the nonmetal, because the nonmetals are fixed charge. They're going to be negative, but they're fixed charge. And the sum of the negative charges has to equal the sum of the positives, because that's this neutrality thing I keep harping on. So chloride is -1, like we saw earlier, 7 minus 8, -1. And notice that there are 2 of them in the formula. So that's 2 -1 chlorides. And there's only 1 iron canceling that. So if there's a -2 overall on the chlorides, iron here must be a +2. So we would write this one as iron 2 chloride, all right? And that Roman numeral is critical. Iron here is a +2 iron. It's connected with chloride. So iron Roman numeral 2 chloride would be the best name. But you wouldn't call it just iron chloride, because iron combines with chloride in different combinations, and here's one of them. This is iron 3 chloride. 3 -1 Cls combined with 1 iron. The iron here has to be +3 to balance the -3 from the chlorides. Iron Roman numeral 3 chloride would be the name. So that way, if I said to you, hey, go get me some iron chloride, I mean, you'd go back to the stockroom and you'd be like, what the? There's different combinations, right? But if I said iron 3 chloride, you know that I meant FeCl3. Iron 2 chloride, of course, would be FeCl2. Here's another one, Fe2O3. So again, start with the nonmetal, which is oxygen. Oxygen is O-2, group 6 minus 8, -2. Oxygen's -2, and there's 3 of them. So 3 times -2 means that there's a total of -6 on the nonmetal side. And that means by default, then the irons are going to have +6 to balance that out. So notice how I figured out the total negative charge, and then I just realized that the irons in this case is going to balance that out with +6. But there's 2 irons, and irons will distribute the charge evenly on what we're going to be studying. So if there's +6 total and 2 irons, each of these irons is going to be positive 3. So this compound here, iron 3 oxide, would be the name of it. All right. So just realize that iron 3, that 3 means a positive 3 iron. It doesn't mean 3 irons or anything like that. It doesn't mean 3 oxygens. It means it's a positive 3 iron. And because oxygen is always negative 2, we can balance them out and figure out what's going on. Let's say we wanted to figure out the formula for copper 1 bromide. So we're going the opposite direction now. All right, no problem. Copper Roman numeral 1 means copper plus 1. Bromide is still same rules as before. Group bromide is in group 7A, so 7 minus 8, negative 1. So copper 1 bromide, we want to balance the positives and negatives, and you can see it's done naturally here. CuBr would be the formula. 1 positive 1 copper, 1 negative 1 bromide. No problem. Copper 1 oxide, we would do in a similar system. Now again, copper 1 means copper plus 1. We've seen several times oxygen still negative 2, group 6 minus 8, negative 2. Now though, to balance out the positives and negatives, we're going to need extra positive to balance that negative 2 charge. So we're going to need 2 positive ones to balance that negative 2. The formula for copper 1 oxide, Cu2O. All right, it's all about balancing those crazy charges, as you can probably see at this point. You don't have to have copper 1 though. Again, copper is one of these variable charge metals. So copper 2 bromide, the copper 2 tells the chemist that you've got a positive 2 copper. Bromide is negative 1, just like it was in the first example. So now we need to balance out the positives with the negatives. We need to have extra negative. 2 negative 1 Brs and 1 positive 2 copper, CuBr2. So hopefully you can see how this is really cool. Those Roman numerals are really important for the variable charge metals. And again, it's everything that's not, all the metals that is, that are not in groups 1A, 2A, or the stairs. And the Roman numeral is really important to tell what the charge is. If you're starting with the formula, use the non-metals to see how this all works out. Polyatomic ions are something that pop up a lot in chemistry. Polyatomic, poly means many, many-atomed ion, all right? And polyatomic ions are just pretty stable combinations of atoms that come together. They usually have a negative charge. Once in a while, they'll have a positive charge. And they're super common. They're all around us all the time, and you've got to become familiar with them. Polyatomic ions are always ionic. They're never covalent, so they're always going to have, as I said, positive or most of the time negative charges, and they will combine with other fixed charge or variable charge metals. And you need to know how these crazy things work. This is a list of some of the more common ones there on the left-hand side. We'll talk here in a little bit, for example, about nitrate, and we'll talk about different ones. Cyanide's probably one you've heard of before. Some of these I'm sure are things you've heard of, but anyway, they're really important to know. In lecture, I'll talk about Nick the Camel, and that's one way that you can fairly quickly kind of come to power with how these things work out. You can also make flashcards if you want to, but you've got to be familiar with how these things work out. They're kind of a pain. I apologize, but you've got to figure out how they all happen. Here's some examples of problems you might see with polyatomic ion. So here's an example, TiNO3. This is titanium 1 nitrate. So titanium 1 means that first of all you have a variable charge metal because there's a Roman numeral, and the Roman numeral tells you what the charge is going to be. Titanium, a transition metal here, is going to be positive 1. Now nitrate is one of the polyatomic ions. It's not an element turned into an IDE. Nitrate, if you look on that list, is NO3 with a negative 1 charge. So a nitrogen, 3 oxygens, and that whole thing has a negative 1 charge. But once you know that, then it's the same game. Balance the charges, make them neutral. 1 positive 1 titanium to 1 negative 1 nitrate, TiNO3. Notice that if you have a polyatomic ion, you're going to have more than 2 elements present. So in this example, we have titanium, nitrogen, and oxygen. In the other examples we saw, we only had 2 elements present at one time. That's a hint for being able to see a polyatomic ion is present. Sodium sulfate is another example of a polyatomic containing species. Now sodium, one of the fixed charge metals, always +1 because it's group 1A. Oops, 1A metal. Anyway, sulfate is a polyatomic ion with a -2 charge. So we need 2 positive ones for 1 -2 sulfate. Sodium sulfate is Na2SO4. Tin 2 hydroxide is another example of a polyatomic. Now this has an IDE ending, and if you're new to the world of chemistry, you might think it's an element, but hydroxide is actually a polyatomic ion. It's OH-. We're going to talk about that a little bit more here in a little bit. Tin Roman numeral 2 means that it's a variable charge metal. Tin is SN with a +2 charge because of that Roman numeral. And because hydroxide's -1, you're going to need 2 hydroxides for every tin. But notice the formula. If there's more than 1 polyatomic ion, you do use parentheses. So 2 hydroxides, you'd write SN parentheses OH parentheses 2. If you just wrote SNOH2, it would look like 2 hydrogens but only 1 oxygen. And you do want to have 2 hydroxides here with 2 oxygens and 2 hydrogens. So use parentheses with more than 1 polyatomic ion, but only if there's more than 1. If there's only 1 polyatomic ion, like on the first 2 examples, no parentheses. Only use parentheses if there's more than 1 polyatomic ion. If you wanted to name FePO4, first of all, you have to realize that phosphate is PO4 -3. And again, you can see that a polyatomic ion is there because you've got more than 2 types of atoms. You've got iron, phosphorus, and oxygen. So phosphate, -3, there's one of them to balance an iron. If phosphate is -3 and that one iron's going to cancel it, that iron has to be a +3. So this compound, iron 3 phosphate. The iron balances the phosphate. The +3 iron balances the -3 phosphate. But again, you have to recognize you have a polyatomic ion, more than 3 types of atoms, and you have to know the charges of the phosphate so you can figure out what the iron's going to be. You bet there's more than 1 combination of iron and phosphate. Here's iron 2 phosphate. Now, phosphate is still -3, and there's 2 of them. So there's like -6 from the phosphate side. That -6 on the phosphate is going to be balanced by a +6 from the 3 irons. And if +6 is distributed evenly amongst the 3 irons, and it will be, each of those is an iron +2, or iron Roman numeral 2. So this one's going to be iron 2 phosphate. So that way, you have to say, if you're a chemist, do you want iron 3 phosphate or iron 2 phosphate? And it does make a big difference. Here's another example of one. This is CrOH6. We saw earlier hydroxide is a polyatomic ion, OH -1, and there's 6 of them. So that must mean that we have a chromium +6, or this would be chromium 6 hydroxide. And again, notice how if you have more than 1 polyatomic ion, you put them in parentheses, etc., etc. But the polyatomic ions are the key to determining what the charge is on the metal. So you've got to know your polyatomic ions, you've got to know the formulas, you've got to know the charges, etc., etc. I'm sure you know all the things I'm thinking. Fascist chemist. Acids and bases, last thing we're going to talk about, are a great source of energy for chemical reactions. You hear sometimes weird uses for them in the media, but in chemistry, acids and bases are super helpful. Bases, we'll talk about first. Bases are nothing more than a metal combined with that hydroxide. And we saw that hydroxide is that OH -1. So if you have a metal and a hydroxide coming together, you've got a base. So here's some examples, some common ones. NaOH, sodium hydroxide. AlOH3, aluminum hydroxide. Now sodium was positive 1 and aluminum, one of the stairs, positive 3. So you can see how the number of hydroxides changes to balance out the type of metal. Zinc is also one of the stairs. It's a positive 2, so zinc hydroxide would be next. But the last two there are Roman numerals with them because those are variable charge metals. Hydroxide, always negative 1. So if there's 3 hydroxides with an iron, that would be iron 3 hydroxide. And with the manganese there, you've got 2 hydroxides. 2 negative ones must be balanced by a positive 2 manganese, manganese 2 hydroxide. Acids provide an H plus to reactions, and that's the energy. And we'll talk more about this in the regular chemistry classes. Sometimes the H plus is listed as H3O plus. That's H plus with the water, but you don't have to worry about that. But the important part is, at least for right now, acids are going to be listed with that acidic hydrogen first. So if you have an acid without an oxygen, they're not too hard to name. You use hydro plus some kind of base name plus ic acid. And I'm sure that's as clear as mud. So let's look at some examples. HCl is probably the most common acid. There's no oxygen there. Notice that chlorine makes that different from the other acids listed. So chlor would be the base. So you call this hydrochloric acid, hydrochloric acid. And the next one has a sulfur as the base, so there's no oxygen, so hydrosulfuric acid, hydrobromic acid from the Br, hydroiodic acid from the I. And again, notice how H is listed first on each one of them because that's really important to chemists. There are lots of acids, though, that have oxygen in them, and those get a little crazier. And in a nutshell, you have to know which one of the oxygen-containing species is the most common. And in this example, on the left-hand side, the one with chlorine and oxygen, the most common form is ClO3. That's the chlorate polyatomic ion. The most common acid gets an ic acid. Then as you take away an oxygen, it goes from an ic acid to an us acid. And if you take away 2 oxygens, hypous acid. On the other hand, if you add an oxygen, which happens sometimes, then you have a per-ic acid next to it. So this gets a little bit weird. Here's examples of the 4 hydrogen species. So again, you've got to know which one is the most common, or sometimes called the base ion. And for chlorine, it's ClO3. So if you add an H to it, an H plus, it becomes chloric acid. 1 more oxygen, perchloric acid. 1 less oxygen than the base would be chlorous acid, and 2 less would be hypochlorous acid. There's a handout that I would ask you to look at. It's called Common Polyatomic Ions and the Corresponding Acids, and it talks more about how to find the base or the most common form of these things, and it also gives some hints. Now, we just went through the chlorine example, but you can see there's also similar things for sulfur. So sulfuric acid is the most common. Sulfurous acid, which isn't as common, has 1 less oxygen. And nitric acid is most common with nitrogen, but there is a nitrous acid, phosphoric, phosphorus, hypophorous acid, etc., etc. You get the idea. So this should give you a good start when it comes to nomenclature. If you have questions on anything, definitely let me know. We'll take care of business. Rooting for you. Good luck with your lab.